Good afternoon, everybody, and welcome to today's lecture. So I'm going to start by just giving some background info. Now, our solar system is made up of millions of stars, planets, and a sun. However, only one of those planets has the component necessary for life, and that is planet Earth. However, our planet is in turmoil, facing issues like water pollution, land use change, climate change, ecosystem collapse, and overfishing. Today's lecture, we are going to focus on water pollution. And speaking to us is somebody with a PhD in zoology. He is a senior lecturer at the University of the Free State Department of Zoology and Entomology. His research focuses on molecular biology, biomarkers, and environmental toxicology. His underlying motivation for environmental toxicology is to contribute to the climate change discourse by conducting work on the combined effects of metal toxicity and increasing temperature. He has a publication record in peer-reviewed national and international journals, is a member of the Society of Environmental Toxicology and Chemistry, or CTAC, and since 2013, has been serving on the editorial board of the Bulletin of Environmental Contamination and Toxicology. He also acts as a reviewer for numerous journals. So with that, ladies and gentlemen, let's welcome Dr. Patrick Otomo, who will be speaking to us on river pollution in the Free State province of South Africa with a case study from the QwaQwa region. So Dr. Otomo, it's over to you now.
Thank you, Aisha. I hope I am audible.
Yes, you are.
Thank you. Do you have the visual? I've just shared my screen.
Yes, we can see.
Okay, thank you.
Thank
I
you.
wish to thank Share Screen Africa for giving me this platform. I've attended some of the events before, but it's the first time I'm here as a speaker, and I couldn't be more happy. So thank you. Below you will see some of the sister institutions, but also some of the founders who've contributed to this research. And as already announced, I'll be talking about river pollution in the Free State province of South Africa, more specifically in the region where I'm sitting from here. I'll tell you a little bit about it in the QwaQwa region of the Free States, and that's found in the eastern part of the province. So just trying to get the slide to, got it. So the QwaQwa region, as already indicated, is found on the eastern part of the province. I'm just going to activate my laser pointer here. So this is the Free State. So we are part of what's called the Maluti Akufong municipality. And right here in the corner, you have the QwaQwa region, which is right here in orange, although here it's presented as the Putali Chaba, but this is more, Putali Chaba is the center of business right here at the center of the image. And the region is tucked in the foothills of the Drakensberg, and we usually refer to that part of the Drakensberg as the QwaQwa Drakensberg. And it is part of one of 8 South African biodiversity hotspots. It's also part of one of the world's 200 most important ecoregions. Okay, so I am currently seated on the QwaQwa campus of the University of the Free State, which is just a stone throw away from where most of the sites I'll be talking about really are. And you can see from the pictures, especially this one here, the far right one, that our winters tend to get really, really grueling. And you will see how it's going to reflect in some of the findings I'll be sharing. If you're interested in finding out more about our institution, at the bottom you have a screenshot of the official university website. You can always follow, search for more information on the website. Now, moving on to the first case studies, I'm going to present 3 of them, okay? And I'll try and do it in a paced way, but not take too much time as well. So the first case study is going to be talking about local wastewater treatment plants, at least one for this this first case, and the effect on macroinvertebrate assemblages. Okay, the study was conducted by former master student of mine, Miss Posha Musoloane. Okay, about 10 years ago, the understanding or the result of a report had revealed that 60 out of 824 wastewater treatment plants assessed in South Africa, and that's only less than 8% of them were compliant, meaning they were doing their job as they should, right? And that's when I joined the institution 3 years after that report was published. I decided to look in a bit into this wastewater treatment plant story and how it was practically affecting river ecosystems. Okay, so Portia was one of my first students working on what I'm going to take you through now. Okay, so one of the wastewater treatment plants that we focused on early on was the Chaba wastewater treatment plant. So the wastewater treatment plant of the city where I'm speaking from, and the part of the work that I'm going to present now is basically summarized on this picture here. What she did is we went to the discharge point, so basically where the water after treatment, okay, the water that is supposedly treated by the treatment plants is to be discharged into this receiving watershed here, which is called the Eland River. We decided to sample invertebrate or macroinvertebrate assemblages before, about 100 meters before and 100 meters after the release point or the discharge point, and we did it on both the right bank of the river and the left bank of the river. So that was the premises of the study. We put in pitfall traps, and you can see what was in there: 75% ethanol and then 25% ethanol glycol. And after about a week, the pitfall traps were collected, and then the student took a month or two, maybe more than that, to basically go through the data and try and make sense of what was in there. Okay, but for the sake of time, I'm not going to get you to the detail because it gets cumbersome. But I've summarized it in a way that will be easier for all of us to understand. Okay, so I'm going to move on to the findings of her study, and it was a seasonal study. She did it. She sampled for over a year, seasonally. Okay, so in summer, which was the beginning of the study, here in blue. Okay, so this is a graph of abundance. You can also talk about frequency of observation. So what you have here is 600. On this side is the abundance, and then here it's broken down in terms of before in blue, that is before the release point, and after in orange, that's after the discharge by the wastewater treatment plants. And you can already see here in summer that there was a slight decrease in the abundance of those macroinvertebrates right immediately after the release point. And this is in the riparian zone. Okay, so these are the insects right by the edge of the river. And then moving to autumn, same pattern. You can see the difference is slightly pronounced, but that same trend you can see. And winter saw a shift, a little bit of a shift, but you can see that the numbers generally decrease because, as you've already seen, most of our winters are really cooling. Half the time we're probably below freezing temperature, so it's not a good time to sample insects really. So that wouldn't be a true representation of what the insect diversity or abundance would be. But then when the temperature increased, sure enough, in spring we had this same trend where clearly you can see whenever the wastewater treatment plants after the release point, there is sort of an effect on the abundance of the micro invertebrate diversity or the numbers, so to speak, in the vicinity of the river. Now, if that wasn't already a sign that something was wrong, the sampling looked like I called it a end party when I was talking to a colleague while preparing this thing. So you can see the proportions here in all the graphs now represent the proportion of ants, okay, in the samples, and they were anywhere between 43 to 87%, depending on the season. And that already showed you when you have such a skewed representation of one group or one type of organisms, you know that your environment is highly disturbed. Okay, so not only the findings here highlight the fact that the river already, or rather the wastewater treatment plants had an effect on the assemblages or the of the abundance, and sure enough the makeup of the different macroinvertebrate assemblages along the river, but also the environment itself already outside. If we were to remove the effect of the wastewater treatment plant, was already highly disturbed. Okay, so that's something to remember there. I went through the literature to try and show you what something more conventional will look like. This is a study in southwestern India, and they did pretty much the same thing. Okay, I have altered the data a bit because they represented more than the pitfall traps that I did. They did berries and winkler extractions, but here represented in green, I only have the findings of the pitfall trap. And by comparison, look where the Formicidae, so the ant population basically is in their study. It's really nothing compared to what we have here, where the ants basically take over. So that tells us that the environment here down the road from where I am, yeah. By the way, that wastewater treatment plants, it takes 5-minute drive to get to the study site. So really bad in terms of disturbances from not only the environment itself, but then the wastewater treatment plant kind of becomes a compounding factor, on top of that. So that was case study number 1. I'm going to move to number 2. Okay. Now in this one, we still stayed with the wastewater treatment plants, but now we had 2 of them, and now we moved into the river and looked at how that will affect river quality and what other implications there could be. Okay. So you already know the first one that I just presented. So in this case, we added a second one, still in our municipality, but outside Putadichaba. Harrismith will be downstream the main river, about 50 km from here. And we went to that wastewater treatment plant. And Mbui Moloi, who is also a former master student of mine, did more or less the same thing as Portia had done, but he sampled the river in the water. So he will go 100 meters before, collect water, that is before the discharge point, and then go 100 meters after the discharge point and collect water samples. And what he did also was to collect from the wastewater treatment sample itself. So here in Putadichaba and 50 km away in Harrismith, he will also collect what we call the influence, that is the raw water, the raw used water, the sewage water that hasn't been treated. He also compared that with what we call the outfluent or the effluent, the water that is eventually released into the receiving river. Here we have the Velre on the picture. It's called the Nieuwe Jaarspruit in Harrismith, and here it's the Eland River that I had already mentioned. And moving on to the findings, okay, and then the focus here was on metal analysis, both the water coming to the plants and being released, and the river water as well, 100 meters before and 100 meters after the release point. Okay, so this here is a picture of what we call removal efficiency. So this sort of analysis help us to see and measure graphically, empirically, how much of the metals is removed from the water by the wastewater treatment plants. Now the good news here is everything above here indicates that the wastewater treatment plant in some measure could do its work. But the bad news is everything below here not only indicates that the wastewater treatment plant couldn't remove these metals, but because they're below the zero line, so it's not neutral, these metals were actually added through the treatment process that is supposed to remove them. These metals were added to to the wastewater treatment plants, to the samples that the plant was supposed to treat. So the sewage water was enriched in a way by more of the metals, more so than it initially came to the plant with, which is really alarming. Okay, considering so these five metals, iron, manganese, nickel, cobalt, and arsenic were the ones concerned here. Okay, and I'll come back to that after a while. But I want to take you to another set of results. So what the student did here now, this is focusing on the water. Okay, remember this is the story about collecting 100 meters before and after the effluent discharge point. Here we have the Eland River. This is on the Putadi Chaba side, and on the right hand side of the table, this is the Wilre on the Harry Smith side. So now the question then was here to find out once the water is released into the streams, both these rivers, do we observe a change in the metal concentration? The answer is yes. And the answer most often, okay, probably 95% of the time, the concentration of the metals increased for all these metals, or for all these metals that I've highlighted here or encircled here. Probably not. Put what rectangles around them, not quite circles, but I guess you follow the drift here. In the case of the Wilre River in Harry Smith, for instance, all the metals across the board were enriched. Okay, it's shocking, for instance, to consider, for instance, before discharge, the river itself, okay, didn't have any copper, for instance. But then all of a sudden, when after discharge, when the wastewater treatment plant released its effluents, all of a sudden there was some copper in there. Okay, so really alarming findings again. But then the question usually is, okay, the wastewater treatment plant is not releasing totally clean water, but how does it compare to the limits? Because we have this threshold that are, that are supposed to kind of help, that is supposed to help them, watch out for those concentrations they shouldn't allow. So when we look at the threshold levels, these were the metals now in the concentrations and encircled this time in blue were the ones that were beyond the allowed threshold. Okay, but then from a purely chemistry perspective, okay, this would make sense. But in biology, especially when you deal with toxicology, all these metals have the potential. Actually, all these metals would bioaccumulate in things like fish, frogs, snails, and anything else in your system. So what that means is, even if it's below threshold concentrations of these metals that are being released into the river, but because it's done regularly at in a sustained manner, the fish eventually is going to bioaccumulate any of these things, actually all of them potentially, to the point where it will actually go beyond the threshold that we are trying to avoid eventually. So this chemically it might make sense, but biologically speaking, when you're dealing with things that can accumulate these things over and over again, and this thing will add up over the days, the weeks and months and years, you still have a big problem in your hands. Okay, so this was more or less what we found. And but now I don't want to make it sound like QwaQwa is unique, okay, in this regard. Okay, here very interesting title about Cape Town having a poo-poo problem, sewage problem. Here we have Durban and we have Joburg. Now I chose these cities because these are major cities in South Africa. I mean, these are reference cities that we all know about, even from outside South Africa. And this news clipping here says that half of South Africa actually is drowning, okay, in sewage, okay. So it's a problem that is not unique to our part of the country or to our province, okay. This is being observed everywhere. And by the way, when it says 1 week ago, this was really 1 week ago, okay. And this was really 3 weeks ago. I copied these fresh from the news yesterday as I was compiling my talk, okay. So that gives you then an idea of what we've done when it comes to wastewater treatment plants and the stress really they bring onto our rivers, okay. Now, moving on to case study number 3 and the last one. I hope I'm not going too quick. So this one is going to look at organic macropollutants in our local waters, okay? But then they might still be, most of them would probably enter the system through wastewater treatment still, but they could be of in your region really. But the only how am I going to say, the only criteria, one of the key criteria that make them uh, macropollutants is that they have to have anthropogenic origin. So it has to be as a result of human activity. So a macropollutant or macropollutants in general will be described as biological or chemical contaminant that would enter our ground or surface water in trace quantities. Typically, it would be lower than the microgram, really. Okay. So what we did here, we went to 3 of these major rivers in the region. Okay, one of them right here is actually where the wastewater treatment plant in the CBD, in the center of town. This is where that study happened. So we went and collected wherever you see a red arrow. We collected water from all of those places. Here up in the mountain, it was as high as 2,200 meters and as low as roughly 1.7, 1.6 thousand meters. Okay, and that's basically the gradient you have when you go from one of our highest sampling sites here to the lowest here. Okay, so and then we went and analyzed macropollutant. Now for this one, I had to connect to some of my collaborators. The half the team here on the screen is from Germany. For this one project, the colleague here, Marinda, was the PI, and everybody else here except for Nduduzo, who is one of the master students on the project, who was actually he's submitted his master's thesis and is awaiting results. But the 3 other collaborators were from the Technical University of Dresden in Germany. Okay, and you can see they in action taking samples and taking readings of the water and stuff, and that is summarized here. Okay, so I'm going to explain quickly. So here on top you have the sampling site. Okay, to the left, as you go from left to right, you move up the mountain. Okay, so you can see that the red, okay, so the bad effect is normally will be concentrated towards the lower part of the river, which are typically much more populated as well. Okay, now here now the color code is whatever is yellow. Okay, green will be below detection level. Okay, for the sake of time, we just gonna remember that. Like yellow would be it is there, but it's not alarming. Okay, it's there, not supposed to be there. Whatever, I'll take you through. It's not supposed to be there, but it's there. Okay, but the concentration is kind of okayish. But then when it's red, it means it's no. Okay, it should be a source of concern. Okay, now analyzing all of these 30 watt chemicals. Okay, so I'm going to focus on the red ones, obviously those of more environmental concern, purely because of the concentration, not anything else. Okay, so we found this herbicide. Okay, it was actually the highest concentrated chemical in the water. Okay, and moving on, we also found, interestingly, some medication in there, medicine. Okay, this was an anti-inflammatory compound. Okay, and by the way, everything here BP, it's just a variation of or by how do you get breakdown products. Okay, byproducts of the same thing basically. So you can see how the representation of this chemical in the river, especially for the B4 here and the BP itself and the BP4. Okay, because remember the yellow means it's there, and here it's even everywhere. Okay, very, very interesting. And then we had some HIV methane in the water as well. Okay, and some methane related to epilepsy. So interestingly enough, how a lot of what we call how do we call methane again in technical terms? Uh, don't worry, I'm talking to myself here. Pharmaceuticals. A whole lot of pharmaceuticals in the system, but obviously there was caffeine. Okay, and I am kind of guilty of that one. My assistant was telling me that I probably go through anything between 3 to 10 cups per day, which could be true. So you have an idea of what then is found in our water systems. Yeah, okay. Really interesting stuff, and the studies are still ongoing. Most of it has been published. Most of it, like the what I shared now, was we only got the result recently, although it's March last year that we went sampling and sent the samples to all the colleagues, took them to Germany to do analysis. So to wrap up, you could see, I'm just gonna talk a bit about the surprising value of water monitoring. Okay, so what we've seen so far, okay, is that your human health, the medicines that we saw, the agricultural trends, and your general environment will impact your water quality at the center here. Okay, so all of these are, somebody, Aisha, in the introduction spoke about land use and all of this. All these things will have an impact. Okay, agriculture will have an impact in your water quality. But then the value of monitoring, if we flip the concept around, okay, if we were, you can clearly see based on the result that I've shared, especially the last bit, okay, if we were to monitor our water regular, we haven't been able to do that. I don't think we have the means now, but that's something that would be interesting, because then your water monitoring can in turn give you information about what is happening at agricultural level, what's happening in your environment, and also what is happening in terms of human health. I was surprised. I was actually shocked to see the chemicals, or especially the pharmaceuticals, coming out of the water, basically informing me of the health status of the people, of the community. Why, when I embarked on this journey, my focus was really water quality. I didn't know that I would come to discover, that AIDS is still a problem, that people are still inflamed, they still deal with a whole lot of inflammation, that epilepsy could be an issue here in the community. Okay, or some of the, I didn't go into it, but some of the chemicals found there came from the agriculture industry. Okay, so there is value in this. Okay, and you will know, because much more recently, okay, I'm talking a year or two back, we were dealing with COVID-19, and that's how wastewater actually helped. Okay, in some cases where teams couldn't be sent into remote areas to test everybody, and they will rely on wastewater. They will basically trace the virus in the water, and this year highlighted here the case in South Africa, and now based on the COVID experience, they're now trying to use what they call sewage surveillance to help spot the outbreak of diseases out there. Okay, so this whole story started with COVID-19. I actually thought that this had been done before. I couldn't find any literature, really not before 2020. But now they're trying to extend it to monkeypox, polio, and influenza. I mean, anything is possible if you can release it, if you can get into water, and we can trace it using DNA or some other marker. We will be able to then more than surveilling water quality, will then be able to tell us more about not just the quality of the water, but also the quality of the lives of the people in the region. So that was me wrapping up and telling you a bit more than the water story, but telling you also about the surprising value of water monitoring. Hopefully, in the next few years, we are given the means and capacity to start such a program here in QwaQwa. And that was it. Thank you.
Okay, yes. So I don't see, Dr. Otomo, I don't see any questions yet in the chat. And I think they are going to ask questions now, but I've got a bunch of questions that I would like to ask you. Because so earlier we spoke about how from the river, a little drop goes to the ocean. And so if everyone, next week I'm going to be speaking about the ocean, and if everyone goes into the, I just want to know, have you checked in terms of the biodiversity, for example, the fish, has anybody checked like the fatty acid profiles, the otoliths or the parasitology, as biotags? Has anybody done studies on those already, just to see how it's affecting them?
Yeah, so part of the bigger project that I showed towards the end, the PI that I showed on the screen, Marinda Avenant, she's actually a fish scientist. Okay, she's doing collections now on the fish on these systems. But you have to understand, when you're dealing with waterways that are so heavily polluted, you don't find anything really. So up the mountains, we found a fish here and then, but once you reach, the edge of town and get into town and past campus and the release points of these wastewater treatment plants, you really don't have much. Okay, but we have parasitologists in the department who've worked in those questions, but unfortunately not in this area. So there still is a lot to do, in that regard.
Mm.
Yeah.
Okay. Okay. Yeah, it'll be interesting. A second question, um, is there or how would you advise them to get rid of medication, old medication?
Whew, that's a difficult one. The thing is, when it comes to micro pollutants as we saw them, our wastewater treatment plants, especially the systems that we use in South Africa, are not designed to remove them. That's the bad news. Yeah, so we're always gonna have them, and unfortunately, like I mentioned now, because this gives us sort of an insight into the health,
Mm.
status of the people of the land. Then, if you're dealing with people who need medication, we have to give them the medication. So that's why monitoring is the only way forward, really. But our wastewater treatment plants, I mean, they can't even remove what they designed to remove. Imagine let alone removing what they were not designed to remove. Yeah, it's
Yeah.
we're not going to be able to sort that one anytime soon. But
Oh, wow.
monitoring will be the way forward. We're just gonna have to try and control. At least we know what we have in the system at all times, and then we can take preventive measures or mitigating measures.
Okay.
Yeah.
Yeah. So once you know what the problem is, you'll be
Yeah,
able to solve
exactly.
it from there.
Yeah.
Okay. And then a last question. Yeah, because I'm gonna give somebody else a chance. Um, can I see which one I can ask? Have you done a comparative study with other rivers? For example, you guys are in inland, but what
Mm-hmm.
about the coastal areas? And for
Mm.
example, a big city like Cape Town,
Mm.
I'm sure, would you think those will be more enhanced? The results will be more enhanced in a city like Cape Town?
No, I remember I showed an example of the situation in Cape Town with the poo-poo problem.
Yeah,
So, and recently I uh, I was an examiner on a thesis from CPUT, and the study area was the Eastern Rivier that goes from the Yonkoshuk Valley past Stellenbosch all the way to Makassar, and
yeah.
in the Cape region. Same issue, same problem, same results. So
Or is it the
we
same? But I
haven't.
mean, in terms of
Yeah,
the levels, the intensity,
yeah, no, it's
abundance.
comparable. The systems are really failing right through, and it's become a systemic problem. Okay, so there is not really. Yeah, it's the same. So we've not done active comparison in as in doing a study here and doing one there, and and comparing them. But we look at the numbers. I keep tabs on my colleagues who are in the field as well, and I can see they're reporting the same thing in their own research. So yeah, it's a
Mm.
nationwide, so to speak, problem. Yeah.
Okay. Okay. I'd love to have a chat more on
No
this because
problem.
else I'm going to sit and talk all day. In the
No problem,
meantime,
Tej.
yeah, but we need to
Okay.
chat more about this because I'm finding the same, well, I'm finding outcomes in the ocean, and I'm talking about the demersal, the benthic environment in the ocean, 500 meters below. We're finding it. That's why I'm asking. So I'd love to chat
Exactly.
further about
Yeah.
this.
No, we'll talk. Yeah, definitely.
But for now, I need to give somebody else a chance, and I see Dr. Mazibedi, you've got your hand up, so I'm going to ask to unmute.
Okay, thank you. So I have two questions, but first I want to recognize Mafi Tladi. Mafi Tladi has joined the session, and he's our former student here at BUST. He did his master's here, looking at some invertebrates in local depression wetlands. So my first question is, apart from looking at diversity and abundance, how else can we measure using invertebrates
Mm.
the impacts of pollutants?
Mm.
And oops, I'm forgetting the second one. So yeah, maybe we can.
Yeah, I can go for this one. What do you think of the second one?
Thanks. Yeah.
Okay, so that's a good question, and what I've done in my online work sometimes, and Portia did that. Okay, her the first case study. Okay, she also took sewage sludge, so not the sludge from the wastewater treatment plant, took it to the lab and tested on on some of the organisms, you know, that we breed in the lab. So you can also do what we call a bioassay, an ecotoxicology bioassay, and we've done that not only with the sewage sludge, we've done it with the water as well, and we've tested it on earthworm, on potworms, which is basically another, you know, type of earthworm, just smaller. We've done it on snails, we've done it on larvae, okay, and mosquito larvae and fly larvae and all of that. And the results basically reinforce what we've already observed, what I already shared. So one of the ways you can do that is to then sample either the soil, the water, you know, take an environmental sample, take it to the lab, and then test an organism. Earthworms will be easy. And by the way, Richard, obviously you and I will need to talk and then perhaps see how to make one of these projects happen. Yeah.
Thank you very much. I was just thinking of maybe looking at deformations in parts of organisms.
Okay.
They can also be indicative of you know, developmental stress that comes with pollution. So you can look at some deformations.
Yeah, definitely. Yeah. So that's what in ecotoxicology we call it's a concept of biomarkers. So after the exposure, you go below the organism, and you can look at anything really. That's as long as it's a response, it's the body reacting to the exposure to that particular, yeah. So, and we also have a battery of biomarkers that we use here, but one of them is to look at tissue and, you know, all kinds of departure from normal state, basically, in your experimental organism. Yeah, you're totally right. Oh, you are muted. I can't hear anything, Richard.
So we have a question from one of the students. Do you want to come? So yeah, just come and stand here. Anyone who's got a question, just raise your hand. You come and say the question from here. The floor is yours. Yes, yeah, just great. Yeah, it's up to you.
Hi, everyone.
Yeah.
Hi, everyone. My question is, why do ants dominate in polluted sites? Thank you.
Okay, that's a great question. Why would they been doing so well, having a party like I mentioned, while everybody else seems to be out of town? So in toxicology, there is what we call a sensitivity distribution. So typically, not all the organisms will have the same sensitivity to other changes in the environment, or let's say the toxic effect of a particular chemical, right? So some will show more of a sensitivity, will be much more susceptible to the effect of the chemical or to the environment, changing the environment, while some will be, you know, they will be tougher. They will tend to dwell there, and sometimes even a concentration that will kill half the things will not harm them at all, or will harm them, but they will still show, boldface. I don't know how to say that in proper English, but you get my point out. So that's the reason why ants are there. It's because they are less, they are opportunistic. So whenever everything is out of town, they move in and take out and enjoy all the resources, and they tend to be hardy and more. And most of them, I remember, were even invasive ants. Okay, so those are those ants that have been taking over the world, and not only in South Africa, but in many other countries. So it wasn't shocking to see them there. And yeah, so we see ants there because they're least susceptible to environmental change, chemically or structurally.
Okay, so my question is, there are some molecules that you actually explained about agricultural waste products, one being acetylchlor, which is a compound which you mentioned as a pesticide. Have they found ways to really trap these heavy metals, and pesticides without it being deposited into the streams? Since you posted those small articles of the big cities having signs of those pollutions, have they really looked at those alternatives? If so, what are they?
Yeah, that's
Before you answer, his name is Freddy.
okay.
Freddy. Freddy. He's one of the
Okay.
most active members of my class. So
Okay, no. I like Freddy. My cousin's name is Freddy, so I feel like family already. So to answer your question,
I just want to add to his question, and it's actually the second question that I forgot. That
okay.
In global change biology, one of the concerns is the increasing human population, and honestly, this pollution and everything comes from that. And just to add to his point, and I think it links with the previous question about why don't we remove these particles. I think the main question is, how do we mitigate? Have we done any experiments? Because the load on the streams obviously is going to increase as human population. And how do we mitigate these levels?
Yeah.
Okay. So Freddy, the bad news is, like I mentioned already, I think while speaking to Aisha, is some of these micro pollutants, you mentioned metals as well, but the micro pollutants, our wastewater treatment plants were not designed to remove them from the systems, okay? But metals, they were designed, okay? The technology that we use currently, old as it is, was designed to at least remove the metals from the water. That hasn't happened. I showed you that sometimes, often even through the process, it becomes worse. Okay, the situation becomes worse. But the good news is, because there are people like you, Richard, and the upcoming generation, and people like me doing research in this, we are exploring possibilities. Okay, I just secured 100,000 rand grant with a colleague in the chemistry department here on campus to address this same question that you mentioned. So he's a polymer scientist, so he has these polymers that he thinks if we do the right chemistry with them, we should be able to trap some of these bad chemicals. We're going to look at metals for a start, iron in the system, and see how it works. And maybe progressively, as we have more ideas and new technologies, maybe then we move into removing micro pollutants. Metals, we have the technology, it's failing us. Macro pollutants still challenging. You've heard of macroplastic, everybody speaks about it, and I'm sure Aisha can give the next presentation on that. But Richard, that's the short answer for the first question that Freddy asked. Now, for your question, it's clear even from the presentation that I gave now, because we had a nice gradient. Remember, we were going from 2,200 meters down to about 1,600 meters down the valley. So most of the sites upstream were pristine. They were cleaner, and then as we moved to the edge of town, as I mentioned when I was talking, and to the center of the city, it became so bad we couldn't even go into the water and try and see if there is anything alive in there, because it was just polluted. Okay, and that tells you, like you mentioned, the anthropogenic pressures on these rivers. So how do we then tackle that and try and mitigate it? We're going to have to educate the people. We're going to have to, as the municipalities, especially in rural areas like this one, are going to have to come up with ways of making sure that garbage disposal and refuse removal is done as it should. Okay, because sometimes after storm waters, after storm events, or people deliberately will just throw things in rivers, because there's a whole lot that needs to be done. But the people need to be educated, but we need also to have the sort of basic infrastructure that's needed to deal with Okay, waste management needs to happen, and all of that is not happening at the moment. So there is no one silver bullet for this problem. Unfortunately, it's going to take a while. But I'm glad to report that at least, although as bad as the situation might be looking at present, we are busy, and I hope the challenge to your class, to the people coming, Freddy and his colleagues, is to make this they lack passion to try and see how they're going to make the earth a better place. Okay.
I just want to go to Nigeria quickly and ask Dr. Ola Leru because she has her hand up for a while now. So I'm just going to ask her a question.
Yeah. Thank you, Aisha, and thank you, Otomo, for your presentation. I'm always looking forward to such classes like this to learn. From what you presented and the data you showed and the figures and the pictures, it gives us the information of what is happening in the waters around QwaQwa region, if I am pronouncing the region well. Now, but I just want to ask these few questions. The issue of some of these heavy metals that you got that were above the threshold, and the fact that it could affect organisms, and you showed us the cascading effects, the fact that it could affect lower organisms and biomagnification and all those stuffs. Sure. But there is this issue of the immediate effects of these chemicals or these pollutants on organisms. Have you looked at it? Perhaps some of them might have even died. Some invertebrates might have died due to the effect of these, because they might have had immediate effect, perhaps affecting their respiration, even their behavior and all those stuffs. I don't know if you have looked at that. And then issues of whether you've experienced some eutrophication in the waters and all those algal bloom that goes that are related with eutrophication situations. So those are just my observations. Thank you.
Thank you. So to start from the end, yeah, the system can be highly eutrophied. So we've had sites where we couldn't just sample because it was just too bad. But because we're dealing with fast flowing systems, like now it's the rainy season now, so most when there is a rain event, or depending on the topography of the region, some of that get washed down, so the problem gets carried away downstream to this river feeds what we call the Val basin system, and the effect is felt in Joburg and like 300, 400 kilometers from here. So yes, we've observed eutrophication at a whole lot of those sites, especially in a highly and densely populated area, as you would expect. But now talking about the immediate effects, yes, we've looked at effect on mortality and survival. This is as immediate as you can go, especially if you select an organism that reproduces within, let's say, a week or two. Okay, so we've done that sort of work. And some of it is published, some of it is on the process of being released. And but if you contact me, I can always share with you some of the data that we have, on the immediate effect on these. We looked at snails, we looked at worms, we looked at some larval stages. We look at frogs even. Okay. And but when you do research actively, sometimes it takes you a while to go back to the data and analyze and write these papers. But the good news from my side, and we have a good number of works even in review now. Yeah.
Thank you so much, Dr. Otomo. I also want the data, please, but we'll chat again.
No problems.
I just want to also ask, before we go back to you, Dr. Mazibedi, I just want to ask the question in the chat that says, with the ants and Geotaxis case study, did you expect positive or negative Geotaxis, and why?
Why does it feel like this is one of my students? Because I didn't even mention the word Geotaxis today. Who is the person asking the question? Oh yeah, no, yeah. I know her very well. She is registered in at our university. So So no, geotaxis, the principle is how any organism responds to the pull of gravity. Okay, so I just want to put it out there. So when you put an organism, for instance, in a water column, instinctively, naturally, it will choose to go either down or up. And if you test over and over again, it becomes a pattern. And so some will go down and some will go up. So the negative, because she used that in the question, negative geotaxis will be when the organism try and fight off the pull of gravity, so they will try and rise to the surface. But now positive gravitaxis is when they respond positively to the pull of gravity and go down. Okay, but that could be on a slope as well. She referred to an ant. So what we did is, but we only tested one ant, one ant species, okay, which is an invasive. It's commonly called the Argentine ant. And what we did is we set up a whole lot of behavioral experiment trying to see if, first of all, to establish the geotaxis, and we established that they will respond positively to the pull of gravity. So they have positive geotaxis, meaning that if you leave them, you put them on a slope, they will go downhill. But now what we did is we tricked them. We put pollution at the bottom of the hill that we created in the lab. So we created a slope, different slopes actually. There was a 15 and 30 and a 45 degree angle slope, and for all the tests we did, we put highly toxic and deadly concentrations of one agrochemical at the bottom. They will, sure enough, they will just go, like, it seems like responding to gravity, that innate desire to go downhill wouldn't even the toxicity wouldn't even deter them. They responded to the pull of gravity to the death at times. Yeah, so that was an interesting find. The students who did the study has finished. She's going to be the degree is going to be awarded now in our next graduation, but the paper is still in the making. So we will be glad to share those findings.
Yeah, I would like to do that one as well, because then don't know, because don't the ants share information, sort of like a broken telephone? So did they not tell the others?
Yeah, no, but that test was an individual one, because we didn't have a system or tracking more than, if you put like a population, it would have been a mess, and they would be crawling and stuff. So, but that's interesting, because we also know that ants are eusocial organisms. So we knew that there needs to be some sort of dynamics if you put them together, but we haven't designed a good advanced test to be able to test groups. Okay, but we still on the question. So yeah, that question we've had it as well. And it will be interesting to see if they can then give the information, especially if we release one and then test him with a group and then see perhaps if something different happens.
Yeah, looking forward to that research. And Don QwaQwa Radebe, when you talk, then I think Dr. Patrick, you can also ask her 5 questions.
Yeah, no, definitely. I'm taking notes.
Okay, so now we're going to go back to Dr. Mazibedi.
Okay, thank you very much. My students have recently set pitfall traps. So, and they have set them on campus to trap the insects, and they have retrieved them, was it last week? Last week. So they're still dealing with the samples. So when I saw a pitfall trap, and I thought they would be excited and have a question about it. So maybe I should ask on their behalf. So you set pitfall traps on the stream margin, on the littoral upstream and downstream of the
release point.
Yes. So what do you think about the insects, the impact of the in-stream pollution on insects that are outside, and why is the pitfall trap the best thing to assess such littoral impacts?
Yeah.
Maybe the question might be put the other way, like, why do we target ground dwelling as opposed to flying? Something towards that extent. I maybe sharing something around that would benefit them.
Yeah, and Richard, also, why didn't we test the insects in the water, for instance, because we were dealing with water issues, right? And so to answer that, in South Africa we have what we call SAS. It's called the South African Scoring System. So it's an agreed upon way of assessing river health and all of that. That is what we wanted to do originally, okay? But then SAS warns you that if the stream that you want to do the SAS in would pose some sort of risk to the students or to the scientists doing the work, you shouldn't do that. So when we got to the site, you know, it was so polluted, I couldn't send, you know, the poor students in there. That's how we came up with doing the riparian zone. Okay, so the riparian zone it's like you putting a sponge next to, you know, at the edge of a plate that has water, so that you don't quite toast the sponge in there. You just put it by the edge where you know it's going to touch. So you know, sure enough, that sponge is going to absorb some of the water from the plates, but it's not going to be soaked, you know, right through it. Well, so what we did is we went and put the traps right there at the edge where the water comes into play, you know, with the edge of the river. So that was indirectly our way of saying of seeing how that pollution in the water will influence the surrounding ecosystem. Okay, so the riparian zone. Now the air would be affected also. I mean, you know, not only the smell and all of that, but some of the flying insects. Talking about the air now, your mosquitoes, most of them would breed, you know, in water. We have a species of fly that we've been using. We call them hoverfly. They have an aquatic life cycle. Okay, the part of it, the larvae will breed in water. So they will also then affect this system. But we couldn't bring ourselves to sampling the air or the water itself or the diversity of these insects in the water because it was just too polluted, and the smell was it was bad. But obviously in more pristine systems you could do that. Okay, Richard. Yeah.
Thank you very much. And I think the ground dwelling insects would obviously have a smaller range and therefore indicate local conditions better as compared to, you know, insects that are highly mobile, like flying insects. So
that's so true.
Yeah, so pitfall traps were, in my view, the best to use, the best technique to use to assess riparian pollution. Any question?
Perfect.
Comments? Maybe to appreciate. I mean, we haven't been focusing on pollution, and this is really a very important complementary lecture to what we've been doing.
Glad to know. Thank you.
So I'm going to send you've got a bunch of compliments in the comment section. So I'm going to send a note with all those compliments that you got for a very well done presentation. Thank you so much. I'm going to be in touch, Dr. Otomo.
Okay, thank you. No problems.
Yeah,
Stay
we'll
in touch.
chat
Thank
again.
you for the opportunity.
And,
okay.
Yeah, no, thank you. And thanks to everybody for joining us. We'll see you next week.
Okay, thank you. Bye-bye.
Okay.